we're going to talk about gravitational and potential energy far from the surface of the Earth. So first we're going to derive the equation. I wanted to go over the actual equations for you to make sure that you have them both in your head and you know what to look for on the equation sheet. When we're near the surface of the Earth, we're assuming that the gravitational field strength is constant. And since we're assuming that the gravitational field strength is constant, we can use this equation, force of gravity equals mass times gravitational field strength. And then we use the gravitational potential energy equation, mass times gravitational field strength times y. So y is the position in the gravitational field. And once again, this is for constant gravitational fields strength. But when we start looking at things far from the surface of the Earth, so things that are orbiting the Earth, we need to use a different force of gravity equation. So we're using force of gravity equals g, which is the gravitational constant, times mass of the first object times mass of the second object. We often write a big M for mass of the big, usually it's a big central object and a smaller object that's orbiting, but it does work for binary stars and things like that, where the masses are closer to the same. And then we divide by the distance between them squared. And this is often written as an R for the radius of orbit. The point, though, is that it's the distance between the centers of mass. The gravitational potential energy equation for something far from the surface of the Earth is negative gmm over d. Now notice that for each of these equations, we're taking the force and we're multiplying by a distance or position or displacement value. So we're taking mg and multiplying by y. Here we're taking gmm over d squared, we're multiplying by the d. And so we get gmm over d. There's a negative sign here, which can be really confusing. The only reason the negative sign is there is because of where the zero is established. Remember that we only care about changes in gravitational potential energy. So it's normal to establish the zero gravitational potential energy at an infinite distance from the Earth or the sun or whatever we're talking about. So that's where the negative comes from, and I'll show you how that comes about. So let's say that we have the Earth here, and we're going to take a pencil and we're going to move it towards the Earth at a constant speed, and we're going to get it all the way to the Earth's surface. We start off at a distance of infinity. This is a thought experiment, obviously. And so at a distance of infinity, we have zero gravitational potential energy. That's where the zero is set. Now, this is backwards of the gravitational potential energy near the surface of the Earth, where we consider the gravitational field strength to be constant, because usually we consider the Earth's surface as zero gravitational potential energy. And now we're considering infinitely far away as zero gravitational potential energy. So it's very important to make sure that you're using the right equation and you think about the zero in the right place. But just like where in our problems for energy, we can set the zero reference line, the zero gravitational potential energy line, anywhere we want. It's not quite like that for gravitational potential energy far from the surface of the Earth, because there is there's like a precedent set, right? Like this is how it's normally done. You can do it other ways. You can set the zero other places, but this is just how it's usually done. So, and this is how the equation's written on the equation sheet. So this is the way you need to think about it. Okay, so back to our pencil. We take our pencil and we place it at infinity. And now we're going to move it towards the Earth at a constant speed. So let's think about our LOL diagram. We have the pencil and the Earth in the system, and we are applying a force on it. Now, to make it move at a constant speed, we have to apply the force away from the Earth, because the Earth is pulling it towards it. And then we're moving it towards the Earth. So the angle between the force and the displacement there is 180 degrees, making it negative work. So we would start off with zero energy, and then we apply negative work on it, and it ends up with negative gravitational potential energy. So then when we write our first law of thermodynamics equation, we have 0 minus work equals gravitational potential energy. We know that work is equal to F times delta X. Now notice that we know that work is equal to F delta X cosine theta, but I already took into account the cosine theta by subtracting right here. So you could add this and then put your negative sign in this part. It doesn't really matter, but just make sure you only do the negative sign once. Okay, so then I know that work is equal to force times my displacement. So we have our force, which is gmm over d squared. I multiply by the displacement that it traveled, which was d, and then I can cancel one of those d's out. And I also have a negative sign because I subtracted the work there. So then we get this equation for gravitational potential energy. Gravitational potential energy equals negative gmm over d. And this is the equation you will find on the equation sheet. Remember that energy is a scalar quantity, and that's our equation. Now this is useful for a couple of reasons. Let me show you how to find escape velocity. So you may have heard about escape velocity. Escape velocity is the velocity required to escape the gravitational field of a planet or a star or whatever. So if we wanted to launch a rocket and make it leave the gravitational field of Earth so that it would not orbit the Earth, then we have to give it a minimum velocity. And that velocity is such that it can get the object to this place where the velocity will be 0, so the kinetic energy will be 0, and the gravitational potential energy will be 0. So let's draw our LOL diagram. So we start off and we have negative gravitational potential energy because we're on the surface of the Earth. If we give a kinetic energy equal to that gravitational potential energy, then we can end up with 0 energy, which is what we're looking for. So we say gravitational potential energy plus kinetic energy equals 0. We plug in 1/2 mv squared, and negative gmm over d equals 0. And then we cancel out our masses, and we rearrange to solve for v. So I'm adding the gmm over d onto this side, and then I'm multiplying by 2 and square rooting. And I get v equals the square root of 2 times g times m over d. And that is escape velocity. So escape velocity is dependent on the mass of the mass of the center object, which makes sense. If you have a bigger mass, it's going to take a larger velocity to get it to escape the gravitational field. Okay, I'm just going to talk you through a problem. So this is a problem, an old problem from 1984 AP test. And it goes through, it uses a couple of different things that we've learned, but we have 2 satellites and they're orbiting the Earth. One has a mass of m and one has a mass of 3m, and they're in the same circular orbit around the Earth's center. The Earth has a mass me and a radius re in this orbit, which has a radius of 2re. So the orbit of the radius of the orbit is twice the radius of the Earth. Then the satellites initially move with the same orbital speed, but in opposite directions. So they're moving towards each other. So first we calculate the orbital speed of the satellites in terms of g, mass of the Earth, and radius of the Earth. And that we've done many times. We start with a force diagram of our satellite, and we see that the only force on it is the force of gravity. We know the net force is equal to the force of gravity, and since it's moving in a circle, net force is mv squared over r. That's equal to gmm over r squared, since it's force of gravity far from the surface of the Earth. Cancel our little m's, which are always the ones that cancel. We cancel one of the r's, and we're left with v naught Then we have to plug in our special things. So we solve for v, we take the square root of both sides. V naught is equal to g times mass of the Earth, which is this big middle mass, divided by r, but r is 2 times the radius of the Earth, which is the given variable that we can use in our answer. So we've got that. Then B, assume the satellites collide head-on and stick together. In terms of V naught, find the speed V of the combination immediately after the collision. So if they stick together, then we know it's an inelastic collision. So we know we need to use conservation of momentum in order to figure that out anytime you have an inelastic collision. We know initial momentum is equal to final momentum. Momentum is always conserved because it's derived from Newton's first and third laws. And I guess it's second and third. I don't know why I said first and third. So initially we have the smaller satellite moving, so it has just mass m and moving at v naught, and it's moving in the opposite direction of the bigger satellite, so that's why it has a negative sign, which is 3m times v naught, and that's equal to their final velocity times their final mass. Their final mass is 4m because they're now stuck together, and this would be their final velocity. So you can see the m all cancels, and then we get 2v naught equals 4v, and so we can solve for v and get v equals 0.5 v naught. So we're going to be going half of the initial speed. Now, on to the question that pertains to what we just talked about. Calculate the total mechanical energy of a system immediately after the collision in terms of g little m, which is mass of, well, it's m, this m here, mass of the Earth, radius of the Earth. Assume the gravitational potential energy of an object is defined to be 0 at an infinite distance from the Earth. Now, this is stated here in this problem, and that means that we're using the equation u equals negative g m over d. Okay, so now we're going to go down here and set this up. We know that the total energy of the satellites once they have collided is kinetic energy plus gravitational potential energy. So kinetic energy is 1/2 mv squared. Gravitational potential energy is negative g m over d. And then I'm just plugging in my special variables. So 1/2 times the mass is 4m times the velocity. I'm using my velocity that I derived up here. No. Oh yeah. I'm using the combination of these two. This is my initial velocity, and then I know my final velocity is half of that. So that's why I got the half of this. That's my final velocity. And then I subtract g times mass of the Earth times mass of the satellites divided by the distance between the two objects. So that would be the radius of the orbit. And then we can simplify this by, we're basically just simplifying this. So simplify, 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 and there we go. There's an example of a problem that you could be asked to do. And that's all we have.